For this class, we're the only one still. I think. But you guys will have to do it next time.
So just write down names. All right. Happy Monday, you guys. Had a good weekend? Okay, at least it's still sunny and warm. No?
I want it to be winter.
Oh, you ready for winter?
I'm ready for snow. I want to go skiing.
Oh, that. Yes.
I don't like me either.
I really don't like how it's like 30 degrees different, cooler in the morning than in the afternoon.
I know. That's Minnesota for you. I don't know. Do I put the heater on? Do I put the air conditioner on? This is the time of the year. All right, let's come back to where we were. I hope our TAs will show up, but we have Andresa. She'll write down names for participation. All right, can you give me examples of adsorption chromatography? Go ahead, Alicia. TLC? TLC is mostly run as partition chromatography because with 2 liquid phases. But we have several forms of adsorption chromatography. I talked about a confusing form last Friday. And I asked, are you all with me? And you were, yes, great. Sophie, you're Sophie, yes. Not Rachel. Sorry. Affinity chromatography, we haven't covered that yet, but we were talking extensively about one form of chromatography, Mitchell, ion exchange. All right, what else? So we talked about one other form that can be under adsorption chromatography. So one other form we talked about. Helic is a form of normal phase, can be run mostly as partition. The other one.
Silica coated with more alumina or charcoal.
So you're talking about helic. Go ahead, Kendall. Yes, hydrophobic interaction chromatography. So remember, we have 3 forms of adsorption chromatography. Ionic exchange, hydrophobic interactions, and then affinity chromatography. We're going to talk about it next. All right, so size exclusion, we haven't talked about it, but what molecular interactions happen, or what type of molecular interactions could be in ion exchange? What type of molecular interactions between the stationary phase and your solutes in ion exchange? So the answer is in the question. Go ahead, Sumili. Electrostatic or ionic interaction, because you have charged molecules. So the interaction is electrostatic or ionic. Either way, it's the same thing. What about in hydrophobic interaction chromatography? In hydrophobic interaction chromatography. Hydrophobic interactions. Yes, it's in the name. We're going to talk about size exclusion and affinity next. So what's the difference between cation and anion exchange chromatography? Go ahead, Sophie. Exactly. So in cation, what are the ions? Positive. And then the stationary phase will be negatively charged. So The naming follows the ions we're exchanging or separating. And in anion, so we are exchanging negatively charged ions. All right, so you guys have the, oh, you don't have the sheets? Oh, okay. You also need to look at attendance as well. Okay. How do you increase the strength of the mobile phase in reverse phase chromatography? First, do you remember what reverse phase chromatography is? What's your stationary phase, polar or non-polar? Right, non-polar, as correct. And then your mobile phase will be polar. So how would you increase the strength? Go ahead, Graham. Increase the concentration of what? Which one, water or the organic phase? You increase the concentration of the organic phase. That is in reverse phase. In normal phase, you increase the concentration of the polar compound. It's the opposite. Okay. What about how would you increase the strength of the mobile phase of hydrophobic interaction chromatography? Do you remember? What's in your mobile phase of the hydrophobic interaction chromatography? You can look back. What's the mobile phase made up of? High concentration of what?
Salty water.
Salt. So salty water or salty buffer. So you increase the concentration by reducing the salt concentration. Okay. What about ion exchange? How would you change the strength of the mobile phase? Increase it. Go ahead. Go ahead. Oh. In ion exchange, you have a buffer. Think about a buffer system. How would you change the consistency of your buffer? By doing what? You change what? The pH. So either increase or decrease the pH, depending on if it's anion, cation, and the molecules within it. What else can you change?
Well, you can increase the concentration of the counter ions.
Salt, yes. So in ion exchange, you can increase salt concentration, you can change the pH, increase or decrease, depending on your molecules and the type of stationary phase. In affinity, we haven't talked about it. You can notice that I didn't put increased strength of mobile phase in size exclusion. This will come. You can't increase strength of mobile phase in size exclusion. Anybody wants to guess why? In size exclusion? Why the mobile phase doesn't matter? Go ahead, Gray. Yeah. Gray.
Isn't it based on size of the particles? So it's just-
Yeah. Yeah, so it's separation based on size. There's no molecular interaction. So your mobile phase is constant, a buffer that your solutes can dissolve in. So you don't change it, you run isocratic elution. Okay, so what's the order of elution in HIC? All these questions are questions that be done in exam or quiz. So we are studying together, okay? So these are very common questions. What's the order of elution in hydrophobic interaction? Exactly. So the least hydrophobic, because the most hydrophobic will interact the most with your stationary. Very good. What about ion exchange? What will come out first? Huh? In hydrophobic interaction chromatography, the least hydrophobic will come out first because they will interact the least with your hydrophobic stationary phase. Okay, now in ion exchange, it doesn't matter if it's positive or negative. What would come out first?
Molecules with the least total charge.
The least charge density, the least charged, the least valence electron. So electron or no electron. Okay. What about size exclusion? Can you guess what comes out first, Gray?
Smallest?
That the largest, but he gets his +2 because we didn't cover this yet. I love the enthusiasm and the courage. It's the biggest. And yeah, Gray, good job. We'll talk about size exclusion in a minute here. All right, good. So these kind of questions you want to ask yourself when you study is like, how much do you know about all of this? Okay. Yes.
With hydrophobic interaction chromatography,
Mm.
and you're trying to change your pH of your mobile phase.
No, salt, not the pH.
For
In-
hydrophobic interaction,
Hydrophobic is mostly done for protein. So you put salt and the salt covered charges. So hydrophobic surfaces on the protein interact with your column.
I wrote that. That was my, sorry. Ion exchange, if you're changing the pH.
Yeah.
Does it depend on the counter ion of your stationary phase that you add?
Yeah, the pH depends on the molecules that you are.
What you're changing it with, like sodium hydroxide to raise or lower the pH, does that? You have to take into account what your stationary phase is.
I don't think I understand your question.
So
What?
if you're swapping fluorides and you add sodium hydroxide.
Well, it's not always swapping chlorides. It is when you.
Does it matter what you're swapping in and out, the ions you use?
It matters based on the type of the functional group on your stationary phase. And it's not always swapping salt ions. Sometimes you protonate by adding acid, or you deprotonate by adding base, increasing the pH, decreasing the pH. You change the ionization state of your stationary phase or of your molecule, and then they loosen the interactions. And sometimes you don't do that, especially if let's say you are isolating proteins. You want to get away from isoelectric point. If you change the pH in a way that the protein precipitates on the column, you want to be careful. So there are so many different things, but I don't want you to worry too much about the details. Here you're learning concepts. If you want to learn all of these details, we need 2 semesters on chromatography, really. Yeah. Okay. Now, affinity chromatography. So we have a solid stationary phase. So this is a form of adsorption chromatography. Here, the interactions are general interactions and specific interactions. So basically, it's like when you think about enzyme and substrate interaction, they are lock and key. So you have interactions that happen between your analyte and a functional group or a ligand on your stationary phase. These interactions can be specific. Let's say you are isolating a specific antigen, a protein. So your ligand could be antibodies for that protein. So that is a specific interaction via hydrophobic, hydrophilic, ionic, that is, hydrogen bonds, van der Waals. So these are very kind of specific interactions. Enzyme inhibitors, this is sometimes used when you're isolating and purifying enzymes. For example, you can find lipases in the market, lipoxygenases, proteases. A lot of these enzymes that we buy have been purified by affinity chromatography. Lectins, these are general ligand type molecules that are used to separate glycoproteins, a general class of glycoproteins. So the stationary phase, you have the support, we call it an inert support, that does not interact with your molecule. It's porous and it has kind of a spacer. Usually it's a carbon chain spacer. And then your ligand that your analyte can bind specifically. So it targets a specific analyte. So any other components in your mixture will not bind. It's very, very specific to a particular analyte. So your stationary phase does not interact with your analyte. It can be made up of agarose, cellulose, dextrin, polyacrylamide, glass. So it has no function other than having a spacer and a ligand attached to it. So once your analyte is bound, now you want to get it out. You can get it out in two elution methods. Either non-specific, you can change the pH or the salt content or the temperature. This disrupts interactions with your ligand. So if you change the pH and the ionic strength, you change the charge on your molecules. You also, if you change the temperature, you can break down hydrogen bonds. If you increase temperature, this you should know from another class, I think with chemistry. If you increase temperature, you reduce hydrogen bonds and electrostatic bonds interaction. So this is not very specific way, but it can reduce the interactions and the analyte will leave your column or your stationary phase. A biospecific, let's say you have antibodies here attached, you can increase the amount of antibody in the mobile phase. So now there's competition between the free antibodies in the mobile phase and the antibodies on the stationary phase. So there is competition. So your analyte can interact more with the mobile phase and leave. So it can be, if you have lectins, like general lectins, you can add lectins to the mobile phase, or you can add antibodies to the mobile phase, or any specific ligand in the mobile phase that is similar to what you have on the column, so the analytes will interact with what's in the mobile phase and lead. So there will be competition. All right, so what type of interactions happen in affinity chromatography? You want to guess? I want you to guess. You get +2 no matter what your answer is. Go ahead, Owen. Van der Waal is one of them. Go ahead, Rachel. What do you want to say? Electrostatic, Razi, hydrogen. So, Sophie,
Is hydrophobic or is it?
it's hydrophobic as well. So all of them. You can have all of these either or 2 or 3. So affinity chromatography is however the molecules interact with each other, non-covalent, they can interact via any of those, multiple of them.
So would it change? Electrostatic specific pollution versus unspecific?
No, not necessarily. In non-specific elution, you can also change, if you have a lot of hydrogen bonding interaction, you can change the temperature, you can break those hydrogen bonding interactions. So whatever the interactions, of course, you need to know your analytes and you need to understand your stationary phase. Then you would know in which direction you would go to break the most prominent interactions happening. Sometimes it's a lot of hydrogen bonding. Sometimes it's mostly ionic with some van der Waals. So you just break as much as you can in the mobile phase. And these are reversible interactions. So none of them are covalent. So all of them are reversible.
And just want to be clear, like
Mhm.
all of these techniques depend on what is the target analyte? What are you trying to separate?
Yes, absolutely. With affinity, usually you're targeting as much of a purification as possible. And it's used a lot in purification of enzymes, of antigens, of antibodies. Yeah. All right, size exclusion chromatography. This is the last mode of separation that I'm going to talk about. So here we have separation based on size. So your molecular diameter, more like. So how that works, you can see here, you have a stationary phase that is porous. So let me draw it so you can see it a little bit. So you have particles of your stationary phase. Particles. When you pack, you're packing specific set of particles. Each particle in your mobile phase has pores. Within each particle, I want to blow this up. Within each particle, you have pores that vary in diameter. And then you have the space within the particles. So your analytes, when they go in, when you inject them on top of your stationary phase, very large, so I'm going to draw it as a square to differentiate. Very large molecules are not going to enter, this is a large molecule, it's not going to enter in any of those because it's too large to fit into the pores. So it's going to travel between, the particles. So those large molecules are going, if you have a chromatogram, they're going to come out first, and we call this in void volume. So the void volume is the volume of the mobile phase that goes within the particles or between the particles. So the large molecules are not going to go into the pores.
Sorry.
The small ones, the very, very small particles, they're going to go in all the pores and be delayed. So those very, very small ones are going to be delayed and they are going to come out in total volume. Total volume, that means the entire volume of your stationary phase in between the particles, through the particles, the entire volume of your mobile phase. Now, anything in between, the size in between, is going to go into certain pore sizes and not into others. So they will be delayed, but not too much. And they're going to come out somewhere in the middle, and we call this elution volume. So the biggest comes out first, and the smallest comes out last, according to this. And your stationary phase, you have so many different stationary phases that you can buy, and they have a different range of size, pore size. So you select the range of pore sizes based on the molecules that you want to separate. So this is something that first thing you need to know what you want to separate, know the molecular sizes, and then select a bed, stationary phase, that will allow separation in the range of your solution. Okay, so we have void volume, we have total volume, and we have elution volume. The biggest molecule comes out in the void volume. The biggest, not necessarily in your sample, but much bigger than any of the pore sizes. And usually we run blue maltodextrin is a very large molecular weight substance to determine our void volume. So when you're running your samples, if you don't know what your void volume is, you run blue dextrin, then you'll determine the void volume. And then we determine the volume of pollution for our substances or solutes. And then we determine something called a constant. But I guess this illustrates what I was drawing here. The red molecules are large molecules, they travel between the particles, and the small ones travel within the molecules, within the pores and get delayed. So large come first, smallest come last. Okay. And then what you do is, well, I introduced void volume, elution volume, total volume. One other thing I did not introduce is the internal pore volume. So which is the total volume minus the void gives you all the internal pores, so the inside of the particles. For us, what's important is the elution volume. And using the elution volume, we calculate a constant, but we must know the void volume and we must know the total volume. Then you calculate that constant and you plot it against the log of standards, then you can find the molecular weight of your solute of interest. We always have to run standards if we want to determine the molecular weight of our solutes. But sometimes you don't really have to determine the molecular weight of the solute. You just use the technique to separate components and collect them based on their size. Any questions about that? Yes.
Like scale.
Relative scale of the operation. You can have analytical scale, like columns that are small and you just use them to determine molecular weight of your component. But then you can also have columns as tall as this ceiling, as wide as, I don't know, and you can use them to purify samples and collect samples. So the range is anywhere in between.
VO void volume.
VO is the void volume. VE is your elution volume of a particular substance. And then V total is the total volume of the, including the void and the internal. Okay, it's a very powerful tool. We use it a lot in our lab to separate. It's one of the dimensions we use to separate proteins. We separate them based on size. Then we take the fraction, we separate it based on charge, and we try to purify a component of interest that way. Okay. So what kind of interactions do we have in size exclusion between your stationary phase and your solute? Electrostatic. Okay, let's hear it for others. What kind of interactions happen when your solute goes through those pores?
I'm thinking none of them.
None of them. There are no molecular interactions that happen. Okay, it's okay. You can still, you get your participation point, but no interaction. You actually want to select your stationary phase as inert as possible, so that the separation is solely based on size. Okay. Yes.
What would be a common mobile phase?
A buffer, phosphate buffer. What do we use? Phosphate buffer, Nigel, in size exclusion? Is it a phosphate buffer that you use? Yeah, like a pH 7.1 molar phosphate buffer. Yeah. It can be water too, right? Yeah, something that your solute can be soluble in too, because you want them to stay in solution as they go through the column. All right, so this is an essential, yes, you have a question? Perfect. This is an essential table for review. Everything we talked about, the different modes of separation are summarized in this table, and you'll find it in your chapter 12, table 3. So why does it do this? How can I? There. Okay, so in an exam, I might give you a scenario, like if I want to separate not flavor, caffeine, or I want to separate carotenoids, or I want to separate protein molecules. And I give you a scenario, and then I tell you what's the separation mode or mode of separation. What would be your stationary phase? What would be your mobile phase? How would you increase the strength of your mobile phase? What elutes first and what elutes last? And then what type of interaction? So this is the set on the top row is a very common set of questions for a scenario, a given scenario. So that's why this is a good summary study table for you to study from. Okay, any questions? Yes.
Is it ever
I-
a problem, doing the size phase separation that your stationary phase does impact, like, an electroport?
Like, do you mean interactions?
Yeah.
We definitely choose inert phases that do not interact. There are some phases that are a combination of ion exchange and size exclusion. I'll cover that in HPLC, but it would be specific. You would know that this is going to separate on charge and size. Yeah, so there is a combination like that. But often you don't want any interaction, you select an inert substance. Okay, well, yeah.
Just for the top one, for the non-polar solvent, it says aqueous methanol acetonitrile. What about those are both things like I consider somewhat polar compared to like hexane.
So methanol is a polar organic solvent.
It's-
Yeah.
it's-
Yeah.
Says non-polar solvent aqueous methanol.
You're right there. Okay, so it is a relatively relative, okay, relative to water. Yeah, but it is a more polar than acetonitrile, definitely more polar than hexane. That's a good point. Can you somebody write it down for me for something to edit in the next edition of the chapter? Okay, good catch. All right, so I want to move on to another topic, which is very essential in chromatography. If you're doing chromatography, you really need to understand resolution. What? Yeah. So again, we started talking about chromatography, and the first thing we said, how do you define chromatography, is separation. So resolution of two peaks or multiple components is very important in chromatography. And sometimes you need to determine how much separation is important for your work. Do you want to separate it just enough so that you can identify? Or do you want to separate it so that you can quantify? So for example, the one on top, you know that you have two peaks. And if you have standards or if you have powerful detector, you will be able to identify them, even though they're not separated. Is there something?
Yeah.
An animal?
It's there. So,
A cockroach?
yeah, like on the wall.
Oh,
Probably not coming.
I hate cockroach. Where is it exactly?
Behind the sharpener.
Okay,
It's far away.
as long as it doesn't fly. I'm traumatized. I grew up in a country that's very humid, and flying cockroaches were a thing. And my older brother traumatized me with them. So yeah, no, he would just when one comes in, he would leave me and hide and not take me with. So sad. Anyway, I hope it doesn't fly. Oh my God, look at it. It's over there.
I love St. Paul. Switch rooms.
Okay, my heart rate is going fast right now. Does it fly?
It probably won't.
How do you take it out?
Higher best.
We still have 15 minutes.
If it comes,
Earlier in the semester, I saw a dead cockroach in a drinking fountain.
Can anybody identify if it flies?
can say it probably won't. It's probably won't.
No.
Probably.
Can you take a picture and then zoom in to see if it has wings?
It has wings. It has wings. It just probably won't.
It has wings?
It just probably won't fly. It's trying to escape.
You know, come closer.
I'm going to grab it and see if it's like I'm not involved.
It keeps going to you guys over there. So does it have wings?
Oh, it definitely has wings.
It has wings.
Yes, yes.
Peter throw at it.
No, but you don't get it. Oh, and like some paper. Don't touch it. Change the clear. It's very defined. Yeah.
Oh, but grab a paper towel to squish it there.
All right. How many points did I get?
Plus two.
Honestly, no, that's valid. That's valid. +5.
+2 to Ovid. Huh? What about you? You help? Okay, he assisted. All right, you guys, let's come back to resolution. This was resolved, so that's good. So it's a good introduction to resolution. What was I saying? Who knows? I don't even know. Yeah, okay. So all right, so separation of the peaks, it depends on what we want to do. So first of all, do we want to, is it a qualitative? That means we want to identify, detect and identify, or do we want to really determine concentration? So if we want to determine concentration and have standards, we need to get the area under the curve. So we want it to be separated as much as is possible so that we can get clear area under the curve. So to develop the separation, we need to know a lot about our solutes. So we need to know information, what's the molecular properties, what is it soluble in, how big it is. So how many components are we resolving? Let's say we are doing pesticides. How many pesticides do we think is going to be in the sample we collected from the field? 5 pesticides, 10 pesticides, how different they are, and then do we want to identify them? Do we want to quantify them, for example? So what is the first thing you would do as a scientist in the lab? You were given a task by your advisor. Let's keep the pesticide example. You go to the field, you collect apples or whatever, and you want to get the pesticides on them. what would be the first thing you do? Don't think about pesticide, anything. What would be your advisor just told you, I need you to identify, quantify, or whatever, using chromatography. What's the first thing you do, Tyler?
You wanna picture or you have to get some idea of where the peak could be on the moon.
So what do you do if you want to do a chromatography analysis and you know nothing? What would you do first
Well, then you'd run the pesticides you're looking for.
before you run?
Research,
You don't know what to run.
research what you're doing.
I bet you money and many cockroaches that somebody had done this before. So you would look up papers to look up methodology. What has been done? That's the first thing. Okay, you might see that there might be 5 different ways of analyzing. Some use reverse phase, some use ion exchange, some use ion pair. Some use a photodiode array detector, others use the fluorescent. What do I do? Next,
Analyzing which one had a similar objective to what you're looking at.
good, that's one thing. What else am I gonna be restricted with? Yeah, what do I have in my lab? What's available? What detectors do I have? What equipment do I have? What columns I can buy and my advisor doesn't yell at me because it's very expensive.
Sample prep. How do you
Yeah.
set out with your test?
Yes, but first thing we agree that you research, you see what's out there. You're gonna find hundreds different methods. Then you can tone it down to what's available in your lab and the cost of running them. And then you will look at sample prep, the methodology used. Okay, from my experience TAs here, if you select a method, is it gonna work, by the way? Never. What do we do next? Yes, there's never gonna be a published method that's gonna work exactly the way you want it to work in your equipment in the lab. So first of all, you identify a method and you say, okay, I can do this in my lab, then I run it and optimize. I might need to optimize the mobile phase, I might need to change my gradient, I might need to do different way of sample prep so that it works, but at least you have a starting place. So choice of a chromatographic separation. You might find, this is a figure in your chapter, you might find 3 articles. Let's say you're looking to separate molecules that have charge. You might find 3 different options. One used reverse phase, one used reverse phase ion pair. We'll talk about that in HPLC chapter. One used ion exchange, either cation or anion. And then you go, okay, what do I do? Then you would go and see what you have available, what columns are available, what columns are cheaper, and so on. This is just to demonstrate that there are multiple chromatographic modes of separation that you can use for a single objective. So, yeah. And then even if you say, okay, I'm going to use cation exchange, there are multiple stationary phases and mobile phases that you can use. So the choice of those depends on what previous literature you found, what information you have on your molecule, also use of interest, and so on. So it gets really complicated. And then you would think, okay, am I going to use isocratic elution? I'm going to build a gradient. How to build my gradient? What would my flow rate be? What is a flow rate? Can you remember? What's the flow rate? You talked about, well, at least the Monday group did in lab. What's a flow rate of your mobile phase? Milliliter per minute. Like how many milliliters of your mobile phase is going through your stationary phase per minute. So it can be 1 ml per minute, it can be 0.5 ml per minute, it can be 2 ml per minute, depending on your system. And it really impacts the separation. the resolution. Temperature impact the separation. How do you think temperature will impact the separation? If you increase the temperature, room temperature, let's say 23, 25 degrees Celsius. I don't know what that in Fahrenheit. Let's
67.
yeah, 60 to 70s, a little bit in the 70s, maybe. Anyway, so if room temperature is, I'm just going to talk Celsius, 23 degrees Celsius. What happens if we increase it to 35 degrees Celsius? What do you think is going to happen to your chromatographic separation in evolution? With higher temperature, what happens to the viscosity of your mobile phase? With higher temperature, viscosity decreases. So what happens to the speed of movement then? It increases. So with higher temperature, you reduce analysis time, one thing. With higher temperature, you can enhance separation of two peaks. I had something, yeah. Let's say you have, at room temperature, you have this going on. Two closely related compounds that have very close similarities and interaction with the column, they're not separated. The width here and the width here is making them not separate. So you increase temperature slightly. You enhance the movement. Then you will get potentially this, if you're lucky. It's not always that easy, but sometimes you will go from here to here. What happened? The width was reduced. So you got sharper peak and they left the column faster. So you were able to separate them with higher temperature. So temperature plays a very important role. Flow rate can also, increasing flow rate can also give you this result as well, because then they leave the column sooner and then you reach equilibrium faster and then they get separated. I'll be repeating all of that later on, but just to give you an idea how flow rate and temperature can be used to enhance your separation and reduce your analysis time. You always, as an analyst, you don't only look for resolution, you also want to look for how fast can I get this resolution, because time is money. So, and then what do I want? Do I need complete resolution, or can I just go with some separation and identification? So then you weigh your options. Before we leave, I'm just going to introduce few terms that we will be referring to quite a bit when we talk more closely about resolution. So retention volume. So basically the mobile phase volume that is consumed or used to get out a particular component. But often in talking about retention, we talk about time more than volume of retention. That means the amount of volume that got the solute out. We talk about the amount of time that took to get the solute out, which is retention time. And often we have a standard to compare to. So those of you that did the caffeine lab, we had a caffeine standard. Those of you that did the GC lab, we had fatty acid standard, that we can look at the retention time of our standards to identify the components. Now, is that easy? Because there are components that leave the column at the same time. The T prime R is adjusted retention time. So the solvent front is usually different from one equipment to another, because you have different tubing size, different differences in length that might lead to different retention time for the solvent front. If you want to compare a compound elution time with another researcher that did the work using a different system, you're better off calculating the adjusted retention time by looking at the time for the solvent front and adjusting that to the retention time. So you get the adjusted retention time. Another important thing is called separation factor, which takes the retention time of peak 2 over the retention time of peak 1. The bigger this ratio, the better is the separation. So I will leave you with that, and then we'll continue. Well, one thing, Wednesday and Friday, we'll have GC lectures with Gary, and then after that, I'll continue with the resolution. Okay, we'll see you Wednesday. Thanks, Obed, for taking care of the. You know, you got +2 for doing that. In your absence, we decided.